Welcome to this video, which will demonstrate how we can find the derivatives of logarithms and exponential functions to bases other than e. So we've already covered how to differentiate exponential functions, base e, Euler's number, and we've done a video that explained how to do find the derivatives of logarithmic functions, base e, which are referred to as natural logarithms. Alright, so what we want to do is extend that to work for any base. And to do that, the formula that I mentioned in our review video becomes important, the one referred to as the change of base. So essentially what we're going to do is, because we now know how to work with base e, is we're going to change everything to base e and go from that as our kind of starting point to find derivatives of other bases. So again, this is the formula that I showed you earlier. If you're finding the log of m to base n and you would like to find the log of this expression to some new base, let's say b, whatever b may be, you take the log of your old argument to your new base and you divide by the log of your old argument to your new base. And that's called the change of base formula. Okay, so if I wanted to find the log of x cubed to base 6, my issue would be I do not have a rule for that yet, so I need to figure that out. However, we will quickly find a pattern here. What we're going to do is change the right side to base e, because the only rule I have right now is the derivative of the natural log of u is 1 over u multiplied by the derivative of u. Using the change of base formula, I could change this expression into the natural log of x cubed, so I'm changing to base e, natural log, divided by the natural log of 6. Well, natural log of 6 is just a number, that's a constant, so I'm going to rewrite this as 1 over natural log of 6, that's a number, multiplied by the natural log of x cubed. And then I will just, anytime use my property from way back when we first started derivatives called constant multiplier. When there's a constant written as a product of a function, you just leave the constant and you take the derivative of your function. So this one would be 3x squared over x cubed. So there's the derivative of log of x cubed to base 6. Alright, now this one, there's no base here, so that's base 10. Switch it to natural log. So it's natural log 5x to the 4th. So natural log of 5x to the 4th. Divide that by the natural log of the old base. So some students who are maybe not as well informed as they should be say, well, there is no base. When there's no base, it's a 10. This would then be 1 over natural log of 10 multiplied by the natural log of 5x to the 4th. So my derivative, constant, leave the constant, and now take the derivative of natural log of u, which is du over u. Alright, now let's see if we can notice a pattern here that would work for the log of u to any base. So this one was base 6, and notice what happened. It was du over u, but then I had to multiply by the natural log of 6 in the denominator. This one was the log of 5x to the 4th to base 10, and I had my final answer was du over u multiplied by the natural log of 10. So I think what you're seeing here is that this is actually very close to the rule for natural log, which is just du over u, with the exception of you have to multiply by the natural log of your base, which is in fact what the rule is. So the derivative of the log of u to any base is 1 over u multiplied by the natural log of your base multiplied by the derivative of u. Now I have that in a nice graphic here. Here is how you find the derivative of the log of u to any base. So the way that I did that last one, we would no longer go through all those steps. We simply do this. If I have y equals the log of 8x to the 4th to base 7, y prime, according to this rule, would be 1 over u multiplied by the natural log of the base multiplied by the derivative of the argument, 32x cubed. Y equals log of, let's do a trig ratio, cotangent x to the 5th. So this is now base 10. Du would be 1 over u cotangent x to the 5th multiplied by the natural log of the base. When there's no base there, it's a 10. And then I'd multiply by the derivative of this. So the derivative of cotangent, there's enough room, I can probably fit it in up here. It is negative cosecant u cotangent u multiplied by the derivative of u. Now, so again, that could be in the numerator or it could be separately out here by itself, whichever you should choose to use. So there's how you take the derivative of logarithms to any base, not just base e now. And to extend our exponential basis, so let's suppose I had this, 3 to the exponent 9x, and I was trying to find its derivative. Well, much like the prior example, we're going to take what we do know how to differentiate, which is base e, and let's use a skill we would have used solving exponential equations. Let's take the log of both sides of this equation. You get to pick the base, so I'm going to take the natural log of the left side, which I'm allowed to do as long as I take the natural log of the right side. Well, now I'm going to just use one of my laws of logarithms here, which allows me to bring my 9x to the front. Natural log of 3. Implicit differentiation, so 1 over, this is ln of u, so 1 over u du. Ln of 3 is just a constant, so it's going to be the derivative of this, which is just 9, multiplied by the natural log of 3, which is just a constant. So you don't need a product rule or anything like that. Dy dx then would be, I have to multiply both sides by y, so this side times y. That would give me, that's gone. Instead of y, you go back to the very beginning, and this is what y is equal to. So my answer here for the derivative of 3 to the 9x is 3 to the exponent 9x multiplied by the natural log of 3 multiplied by 9. Now again, we're looking for a pattern. There is a pattern that evolves out of this. For the derivative of b to the u, where b could be any base, and you're trying to see, and some of you may already see a pattern here, but we'll do one more the long way before we write out a rule that will do this instantly for us every question. Same thing, let's take the natural log of both sides. Again, the reason I'm picking, I could choose any base I wanted, but I'm choosing natural log because I know that to take the derivative, natural log is the best choice because you don't end up with that extra ln of your base, which I'll get to in a second. But technically you do, but the natural log of e just turns out to be 1. Okay, so I'll take the log of the right side. So here, 1 over u du equals x. Oh, I shouldn't have started to take the derivative yet. Just let me erase this. Let me try that again. So what I'd want to do is multiply by x to the 5th here first. So natural log of y, power law of logarithms, x to the 5th, ln of pi. Now take the derivative. So 1 over y dy dx, 5x to the 4th times ln of pi. Dy dx would be 5x to the 4th multiplied by the natural log of pi multiplied by y. You'd have to get rid of the y here. Replace y with what it was equal to in the beginning, which was pi x to the 5th power. So when I write out my derivative, so y, I'm going to put it at the first. You'll see why when I show you the rule here. So my y was equal to pi to the exponent 5x to the fourth. That's not right. What did I do wrong here? Sorry, pi x to the fifth. That was my du. Right, if you look at the beginning here, pi x to the fifth was y. So there's y, natural log of pi, multiplied by 5x to the exponent 4. So what we've just done is took the derivative this time of pi x to the fifth. Notice the answer was pi x to the fifth multiplied by the natural log of pi multiplied by 5x to the fourth. Up here we took the derivative of 3 to the 9x, and our answer was 3 to the 9x multiplied by the natural log of 3 multiplied by 9. So generically speaking, if you don't see the pattern, here's a way to avoid all of those steps and go right to your answer. The derivative of any base to an exponent, now this is when the base is a number, okay, that's important, is b to the u multiplied by the natural log of your base multiplied by the derivative of your exponent. Again, I have a nice graphic here. This is the rule that we would use to differentiate any exponential function, base whatever number you want, as long as it's a number. Now if this is an x and raised to something, then that's a different process altogether. But for bases involving real numbers, now what I was alluded to earlier is we knew before we started the derivative of e to the u was e to the u times du. We had uncovered that earlier before we get into other bases. Euler's number was kind of our first base of choice. Well, I just want you to see that this rule really works for e as well, because the rule would be e to the u times the natural log of your base, which is e, multiplied by the derivative of your exponent, which would be du. Well, natural log of e should be something that you familiarize yourself with to instantly realize, well, that's just equal to 1. And you may say, well, why is that equal to 1? Well, the reason it equals 1 is because of one of those properties I showed you earlier that said that if you have the log of a base to the same base, it will always just equal your exponent. Well, natural log, remember it's not written in there, but it means base e. So natural log of e really means the log of e to base e. My exponent will be 1. So therefore, this has to be a 1. That's why at some point you may see things like this, natural log of e to the fifth. And you would be expected to hopefully instantly say, without touching a calculator, oh, that's equal to 5. Because this is base e and this is base e, it's got to equal the exponent. And that's what happens when you know your properties and laws of logarithms. Alright, so that now gives us the ability to differentiate. I'll just go through our list of transcendentals. We can now take the derivative of trig functions, inverse trig functions, exponential functions base e, exponential functions generically, any base, not just e, logarithmic functions base e, which we refer to as natural logarithms, and a general version of logarithms where it could be any base, which I went through earlier in this video. And those will be the transcendentals that we will cover. There is another set that are called hyperbolic trig functions. We will not get into those in this course, but you may run into them if you take some calculus beyond high school. But I think having this solid background in these transcendentals will set you up to easily be able to add the hyperbolics to your list if you needed them. So thanks for watching, and again, best of luck in your practice with these, and reach out if you have any questions. Thank you.